Day 12, Passage Pathing. With your submarine's subterranean subsystem subsisting suboptimally, the only way you're getting out of this cave anytime soon is by finding a path yourself. Not just a path. The only way to know if you found the best path is to find all of them. Fortunately, the sensors are still mostly working, and so you build a rough map of the remaining caves. Okay. This is a list of how all of the caves are connected. You start in the cave named Start, and your destination is End. An entry like BD means that cave B is connected to D, so it's non-directed, undirected. Your goal is to find the number of distinct paths that start at start, end at end, and don't visit small caves more than once. There are two types of caves: big caves and small caves. So those are big caves, these are small caves. Alright. It would be a waste of time to visit any small cave more than once. So all paths you find should visit small caves at most once. Okay, so I assume they've designed it such that there's no two big caves next to each other, otherwise you could just infinitely go between them. So this is really like a depth-first search problem, I guess. But just fully search everything. Can you allow revisiting of big caves? Alright. And the graph is not too big, so how many big caves do we have? 1, 2, 3. And we've got... Okay. Wait, are we allowed to visit Start multiple times? I mean, it's lowercase, so I guess by the rules, yes. And End... well, no, because they did say... They haven't technically said whether Start counts as a small cave. I'm guessing it says start at start, end at end. Yeah, but if it's lowercase, that means you can only visit once anyway. Okay, so that's not a problem. Alright, so yeah, start and end you can only visit once. Alright. This is basically a graph search problem. Second. Okay, so graph. Yay. I like writing graph code even though it's the same every single time. Let's make a graph class. Alright, how do we do this again? Init self dot, let's call it edges equals, this is undirected. So this is going to be a dictionary which maps a node to a set of neighbors. We want a method of adding edges. Self.edges u.add v self.edges v.add u and that's it really. And then we want a depth first search. But this is a depth first search that returns all paths, but we just return the count of them, don't we? Yeah. So remember how this works. Okay, so DFS, you start with a queue that, say, start and I'm not writing it like I have to think for a second. Hello, cheesed up. What time is it for you? It's 6:35 for me, PM. Okay, so alright, I just write DFS as normal and then adjust it to return the paths. We can also have like a path count 0. So while q current equals q dot and hang on. This is actually a bit confusing. This thing about revisiting big caves makes it... I don't think we really want to write this like we usually write DFS. We want to write it like... I don't know. I guess we can write it like a... Didn't know you code? Yeah. Yeah, I code. Mainly in Python. I like using it to solve these like mathematical type puzzles. I'll just write normal DFS and then look at it and see why it doesn't work. Alright, so current execute.pop, neighbor, for neighbor in, use Greenfoot. Greenfoot. I don't know about Greenfoot. So neighbor in self dot edges current. This isn't going to work because we need to backtrack, don't we? So we actually need to record the path we... okay, no. Just write it fully, then worry about it later. For neighbor and self.edges current. So we need to keep track of what we visited. Visited equals set. Neighbor in self.edges current, we want to... If neighbor in visited, then we skip it. Otherwise, it's probably a valid neighbor. So we want to put it on the stack. Q dot append. Yeah, okay, this makes sense. Q dot append neighbor. Now, we only add it to the visited set if it's lowercase. And the problem here is I don't know how to backtrack in this visited set. Maybe this is the wrong data structure for this, but we'll just carry on like this. So if neighbor dot is lower, that's if it's lowercase. Visitor dot add neighbor. Also, if it's the end, then we have to end there. So if current is end, then we do path count plus equal 1. And then just continue to the next step. So that's almost perfect, except this visited set is like, when we backtrack, it's gonna keep all the visited things that we've had before. We have to remove them. So all right. I think we don't want this. What we want is just a record of the path we're on right now. So path equals that. And then we remove stuff from the path when we're backtracking. So whenever we pop an element here, that means we're on that path. So oh man, I don't know how to do this. Maybe I have to take a different approach. Just write it recursively. Yeah, recursion might actually be the better way to go here. Because this backtracking method doesn't have a way of backtracking because we can't kind of go backwards. We can't remember what we visited and in what order unless we store the whole path that we followed. But all right, let's try writing it recursively. I'll just comment this out for now. All right, so recursive. So path. So this says we want to find the number of possible paths from a given start to a given end, given that we've already followed this path here. Or we don't even need to say that. We could just say given that we've visited these lowercase small caves before, we're not allowed to visit them again. Yeah, I think this is the way to do it. So ultimately, the answer will be when we set start to start, end to end, and this to empty, because we haven't visited anything. But call itself recursively as we do this. So we say neighbors. So for neighbor, hang on. The base check is start equal to end, because then the answer is one, because we're returning the number. Yeah. If start equals end, then return 1. There's only one possible path, and that's just don't do anything. All right. So start is not equal to end. So for neighbor in for the neighbors of the starting point, so we need make a copy of this. So neighbor in self.edge start. So if it's in visited, we're not allowed to. Oh, no, because if it's lowercase. So if if neighbor in visited continue. So we're not allowed to go there. We don't even need to do this. Get rid of that. Are there any other types of neighbors we should skip? No. So this is a valid neighbor. So now basically we want to make a subcall to DFS, which is going to be DFS from this new neighbor to the same end, but this time visited new visited equals visited union neighbor if it's lowercase. Otherwise, if it's uppercase, we're actually allowed to visit it as many times as we want. All right. So we make a recursive call, DFS, with the new visited, which may or may not include this neighbor that we've just added. And that will just return a number, 1. And like, so result plus equal that. So for each neighbor, we add the number of possible paths from that neighbor to the end. Okay. And if we reach a leaf and there's no edges to go from there, that's fine. We'll just get a 0 back because this will be a redundant loop and we'll just return 0. Okay, does that make sense? try it anyway. All right, now we have to actually use the input, so... all right. Left, right equals line dot strip dot split on the hyphen. Okay. And then we want to put that into the graph. Okay, so we need to make a graph. Graph dot add edge left right, and it will add both ways, right to left, left to right. Hang on, this should actually technically include start, shouldn't it? No, but... Alright, we'll just do it like this. If we don't provide a visitor, that means it's the top level call. If visited is none, then just redefine it to be contain just start. Because we visited start, we're sitting on start, therefore we visited it. Yeah, that should be fine. Okay, so we add all the edges, and now we want to compute print graph dot TFS. So we want to start from the thing called start. We want to end on the thing called end, and we don't add a visited. Okay, will this just work? 1034? No, I feel a bit unsure about this. Nope, it's wrong. Okay. Fine. I mean, okay, it runs in time, so I think the algorithm is mostly correct. There's just errors somewhere. So what is this saying? This is saying I want to find the number of paths from this point to this point where we're not allowed to move to any nodes which are in this set. That, in principle, should work, shouldn't it? Is there any catch to that? No. We're saying if it's the starting call, then we just say we visited start. That's fine. If we're starting at the end, then the answer is 1. Yeah. Otherwise, we just add up. So for every neighbor of this start, as long as it's not visited, that means this is something we can go to. And then call the function again from that neighbor to the same end, and we're now no longer allowed to visit neighbor. If it was lowercase. And we find a number of paths from that. We add them all up for all possible neighbors, and that seems right. Okay, let's test it on the test example then. Start with the smallest example they give. Okay, we found 4 parts. The correct answer should be 10. All right. So we only found 4 of them. Let's record what calls are being made here then. So we're doing start to end, we're doing A to end, we're doing end to end. That's valid because you can go start to A to end. That's one path. We're doing B to end, we're doing end to end. Yeah, so start to A to end, start to B to end. Those are both valid paths. And then there's also D. So we've got D where we visited B. Oh. Wait, visited? Oh, no. Okay, no, that's right. So D to N, we want to find the paths from D to end where, oh wait, capital A shouldn't be in there. It's uppercase. Why is capital A in there? There's the problem. So I said neighbor is lower, then we don't add that new neighbor, right? Damn it. How could an uppercase thing ever end up in here? That's why we've got so few paths, because we're not allowing ourselves to revisit a neighbor.is lower. Oh, that. Why didn't the IDE warn me of this? That's a meaningless. That has no side effect. It's supposed to be that, right? That's just calling the method. I thought the IDE normally warns you when you do that. There we go. I just didn't have the brackets. That's a method, but I just called the method like that, which does nothing and has no side effect. I thought the IDE would pick up on that because it's a method with no side effects, so whatever. Okay, 10 is correct. Right, go back to the big example. 3, 4, 6, 3. Correct. After reviewing the available paths, you realize you might have time to visit single small cave twice. Oh no. Okay. Specifically, big caves can be visited any time. Specifically, big caves can be visited any number of times. A single small cave can be visited at most twice. And the remaining small caves can be visited at most once. However, the cave's name start and end can only be visited exactly once each. Once you leave the start cave, you may not return to it, and once you reach the end cave, your path must end immediately. Why didn't they say that in the first part? Okay. Now the 36 possible... Okay. So, you're allowed to pick one small cave and visit it twice. But all the other small caves can only go once. Okay. Shouldn't be too much more complicated, but we're gonna need a... Okay, so get rid of this. So that is basically DFS 1. Now what do we do? I guess we want to keep a count. I don't think it's much worse, but there will be more parts available. So it'll take longer to compute, but the intermediate step will be roughly the same. So we just have to say... Okay, so just make a complete copy of this. So we no longer want to use a hash set. We want a counter, but the count is only ever one or two. Well, so we're not memoizing, but so far it's been fine. But we could memorize because we might revisit paths multiple times with the same visited set. If it takes too long to compute, then we can memorize, but for now it seems to be fine. So if visited is none, then so Alright, visited shouldn't... Don't bother putting start in visited. Here, if neighbor in visited... If neighbor is start or neighbor in visited, we continue. So don't do that. We can just say visited equals an empty set. All right. That should return the same result. What happened there? Oh, because and now we need to oh, I'm typing into... Alright, just hide this for now. We're focusing fixing the FS1. Alright. If neighbor equals start or neighbor visited. All right. Also, if we just say if neighbor is end, then just, we know that's a path, just do that. We don't need to do the base case, and then continue to the next neighbor. So we don't need to do this one, just get rid of that. We'll leave it just in case somehow we arrive at that position, but it won't happen. So, yeah, so we should get the same 3, 4, 6, 3. And now visited only ever keeps track of the lowercase thingies. Alright. Now copy this. Copy it into here. So now, this time, we don't want... I think the simplest thing is just have this to be a counter instead of... Yeah, we can use a proper counter. Visited is counter. All right, so same process as before. Result consider for neighbor and subhead. So if it's start or if it's visited, now this is the catch. So we look at the counter, and if we see any 2s, that means we can no longer visit small caves. We can no longer revisit small caves. So, can revisit small caves equals 2 not in visited dot values. If there's a 2 in there, that means one small cave has been visited twice. We're not allowed to do it again. So here, if it's start or neighbor is invisited and we're not allowed to revisit. Then we skip. Okay. This ends that. Okay, and then here, new visited equals visitor. So we don't do that. We say if it's lower, if you union a counter with, I don't know how counters work. Can you add them together? Let me Google this. Just with the plus symbol? Or do you union them? Imagine you can just add them. Just go to the documentation for counter. Actually quite a lot of methods. Yes, you can add them just using the plus symbol. So it's going to be visited plus, and then it'll be a counter. How do you initialize a counter? You just say neighbor equals 1. So if we got this far, then we've established that either we've never visited neighbor before, or we have, but we're allowed to revisit. Then we add 1 to it. So it either goes from 0 to 1, or 1 to 2. And then we return that. Visited is the wrong name for this now that it's a counter. Doesn't matter. And is that it? It take longer to compute, but it should just give us the correct answer. Ooh, now we got recursion. Depth exceeded. Oh dear. So we can increase the recursion limit to maybe 10,000 or something, but we shouldn't go any further than that. I think we want to memorize. Let's see if we can just get away with. So once I set it too high and I crashed my entire computer, which also ended the stream. But let's just go with 10,000. Still too much? I think 50,000, but I'm not going any higher than that. It's too much. Okay, fine. Fine. We'll leave that recursion limit, but we probably want to... Mem-wise, that would mean... Okay. That means, first of all, we need to... We can't pass a counter in. We have to pass a unique signature. We have to be able to hash the counter, its values. So what we actually need is... a tuple of values. And it's sorted, so it's unique. All right, so... Okay, so... So visited is going to be a tuple of values. And we just pack that into that, and it should be able to unpack them. So we get a counter. If it says, like, we visited this, and maybe one of them is is duplicated, then it will give 1, 1, 2, 1, 1. So it'll count. So we're giving it as a tuple because that's hashable. And then we say, can we visit if 2 is not in the values? And then here... So we should be using counter from now on. Now here's the tricky bit. So we say... New visited will be the old visited, but we append just the tuple with neighbor in it, so that's a 1 tuple. If it's lower, otherwise it's visited. And it will have to be sorted. That it's sorted into the correct place, otherwise it's not hashable. And then sorted, and that has to be a cluster tuple. Otherwise we pass the old visited. That should just be an empty tuple. We don't even need to do this. We don't even really need to make this counter. We can just check if something appears twice. That is... fine. No, we do need a counter for this bit, yeah. Alright, so That's still going to take too long, but it's just now we can actually hash this value. Let's try it again. What? That actually ran. Why? What's the difference? Does it just not like passing around those? We didn't memwise, so why would it be faster? We're just passing a tuple back, to the subroutines instead of that. But why would that matter? It's not increasing the amount of recursion or decreasing it. It's just different data structure. And if we don't memwise, then it shouldn't be taking any shortcuts. Let's see if it's correct. Correct. Why did that work? Well, I also did increase the recursion limit to 50,000. So if I take that out, I think it will fail. I think it's still too much, even with tuple. Oh, no, we didn't even need to mess with the set recursion limit. I think because it's not just because of the number of levels of depth of this function, but also because I guess there's some stack recursion being used just to keep track of these sets. I guess it's using some recursion there. I don't know. I don't know exactly how the recursion counter is used, but I guess it's used for other things as well, not just layers of depth of the function. But if we do that, I guess it's also using some of the recursion stack. So if we tuple it, we remove any, it's a fresh variable each time. And the only recursion really is in how many times this method is called. I mean, what I wanted to do is just do memwise at this point. Like, okay, let's test it. How long does it take? Like a second. Will it go faster if I now memwise? So we just put that decorator basically. Let me just put it here. So cache. So we use a least recently used cache, basically memorizing. Doesn't like it. Oh, no, we just import cache. Yeah, no, we don't want least recently used. We want everything used. We don't want to discard things from the cache. We just want full cache. LRU is used for processes where you're repeating stuff and you want to speed things up by you know, not having to recompute things you've recently dealt with. So keeping things in memory, but it will eventually discard things when things get old. Here, we want to remember everything. All right, let's try caching it now. Instant. It did actually improve it. It went from like 1 second to like 0 seconds. So yeah, caching is good. I mean, 1 second to 0 second, that's a big increase, so... it turns out we didn't actually need caching. Yeah, it was fast enough, but in other languages it might not be the case, I don't know. So maybe some people had to use caching. It's an interesting problem. I got stuck early on because I was writing DFS the standard way, but you need this visited set. You need to write it. You don't have to write it recursively, but it's so much easier to code if you write it recursively, because then you can just write this function and call it again. No having to write backtracking code where you have to look at what you had recently, take that off the stack, go back. Yeah, this is just better. But caching is, if you go down this path, you do need to cache generally, because otherwise you're revisiting subpaths that you've done a million times before, and you already know the answer, so you shouldn't do them again. Like, if you have a big amount of branching, but then it comes together as a choke point and then goes to the end, then you'd be so many times you'd be recomputing subpaths. Alright, that's a good problem. Tough one. I think this will probably be one of the harder ones out of these first 12. Well, we can check. You can't really tell from this, but it looks okay. So if normally you expect like a steady slope, because people lose interest and they stop solving problems after a while. But with 12, you can see there's a drop, and then 13 and 14 it just stays steady-ish. That kind of indicates. I don't know. You can't really measure difficulty from this, because there is a huge factor of people will do the first n problems and then stop there. So, but you can sort of see that 19 clearly is difficult. 21. Looks difficult, but more people attempted it. I don't know. Maybe it was a nice problem. Alright, well, we are halfway there-ish. Just under halfway there. But remember that day 25 is a one-parter. So we are actually halfway there. Alright, I think that's enough coding for today. I need to go get dinner, and maybe I'll do more tomorrow, but eventually it'll reach the point where I could only manage one problem one stream, because there have been problems in the past where it took me like 6 hours, 7 hours to solve one problem. Although that's becoming less frequent, and I don't think it's a case of me getting better at them. I mean, I probably am getting better at them, but I think he genuinely has been making them easier over the years. Like, 2019 was the crazy year of int code, which a lot of people struggled with. Like, that looks really rocky. I mean, you could sort of see. So it was like even numbers were int codes and odd numbers were, or some. Yeah, even numbers were int codes, and odd numbers were general problems. So people who couldn't solve the int code problems wouldn't really probably do any of the remaining int code problems. So all the even numbers. You can see there's some sort of step pattern. Like 18, for example, is an int code. But yeah, that was the infamous year of the int code. That never really happened again, even though he did introduce int code. For those that don't know what int code means, basically it's Eric, the guy who makes this, is really into assembly code, assembly language type puzzles. So he devised this kind of these problems based around where you build a script which reads an input in an assembly-like way, with commands like, if we go to one of the last ones, 24. 22, I don't know. These are not encode problems. Was it the odd ones? Or maybe it wasn't every... Am I thinking of a completely different year? I don't know. Maybe I'm thinking of a different year. Maybe it wasn't 2019. Either way, encode is like you write an assembly code program and then you have to run it. And basically your program is simulating like a kind of Turing machine. It's simulating a computer and how it would behave if it had this input and what output it would receive. And then it gets more complex because you can have parallel programming. So you can have different processes each doing their steps, but then they hang if they don't have the input they need and they're waiting for some other computer to give their input. So you have to simulate concurrency between different machines, but in the correct way. Crazy stuff. All right, we're almost there. I always do a quick check just in case someone happens to be doing Advent of Code, but no one ever is, so it's June. It's not the season for Advent of Code. Season for Advent of Code. Season for Advent of Code. Tis not the season. Season for Advent of Code. Somebody did some Advent of Code 10 days ago. Somebody did some Advent of Someone did one 4 days ago. Shari makes art. Oh no. Yeah, it was in C++. 2022. Looks like I'm arriving at the end again. Welcome in Smap UK. Yeah, I just did 3 problems. I just finished with a recursive depth first search through a graph. Don't know if you remember it. Not too bad. I got confused at first because I was so used to writing depth first search the traditional way. I needed to adjust it for allowing to revisit nodes under certain conditions, which makes it a bit confusing. But I mean, once you write it in a recursive way, it's not too bad. All right, that's it. See you next time. I might do another one tomorrow. We'll see.